Hello friends, and welcome to the channel Derive. Today we'll look at this formula, which I think you'll recognize. It's the area of a circle. But how do we actually derive this formula? And there are a couple of ways to show this. First, we're going to start off with a visual way to show this. We're going to draw a circle. Within this circle, we will draw an infinite number of concentric circles like this. So incredibly many circles, concentric circles within this big circle. And then what we'll do is we'll cut this circle from the center to the periphery. And what we'll end up with, if we straighten all of these circles, which by the way have a width that's infinitely small, so they're basically strings within this circle, an infinite number of strings. We cut them, we elongate them, and we will get something that looks like, if we order them by length, we will get something that looks like a triangle, right? So an infinite number of strings that we have straightened out and ordered according to length. And since it's an infinite number, we can draw the hypotenuse here. There won't be any overlap with the hypotenuse because remember, the width of these strings is infinitely small. So this problem is much easier now to calculate the area of this triangle, right? We have the height, which is the length of the longest ones of these strings, which is the periphery of the circle. So it's 2r pi. Then we have the base, which would be the cut that we made from the center to the periphery of the circle. That in turn is r. You all know that the area of a triangle is the base times the height divided by 2, which in this case would be height times base divided by 2, which is r2 pi. So r2 pi is the area of this triangle, which in turn is the area of this circle. So that's a visual way to show it. Can we show this formula, derive this formula through calculus? Yeah, we can. And we can start off with the hypotenuse here and put it in a coordinate system. It will go from origo, and if we move r in the x-axis, we would reach 2r pi in the y-axis. And that would give us the function of this line, which of course is y equals 2 pi x. But what we're interested in is the area under this line. Remember what I said, that these strings had an infinitely small width and were infinitely many. And every time we add up an infinite number of infinitely small things, we have integration. So to get the area under this line, we have to integrate this expression from 0 to r. That's pretty easy if you know integration, but we will write out the expression. So it would be 2 pi x dx. We can factor out the pi. And the primitive function of 2x is x squared, of course, from r to 0, which in turn is pi r squared minus 0 squared, which is r2 pi. So that's the area under this line, which in turn is the area of the circle. Is there another way to understand this concept of concentric circles that we then straighten out to strings to get the area of the circle? Well, yeah, if we start off with these circles or strings being a bit thicker. So then it's a bit easier to demonstrate. We can draw the circle again. And then we draw a circle within this circle. And then we cut this circle. We straighten it out. We would get something like this from the cuts. But of course, in the end, we can transfer this cut here, because now it's a trapezoid. We can transfer it to this side, and we'll end up with a rectangle. So we'll have this rectangle. The width of this rectangle we can set to dr. And the trick now is, as I've said before, that we made the width infinitely small. So dr is infinitely small, which would then result in an infinite number of these concentric rings within the circle. So we'll have rectangle here, rectangle here, rectangle here, and so on. And the biggest ones of these strings or rectangles with an infinitely small width would have the length of, if we set this radius to r, it would have the length of 2r pi. But an arbitrary rectangle would have the length of 2r pi. So the longest would have a length of 2r pi, but an arbitrary would have a length of 2 small r pi. What we want to do now is add up all of these rectangles from the center to r, because that would give us the area of the circle. What we'll end up with is a very similar expression to this one, or actually the same expression. From 0 to r, remember, big R is the radius of the circle. So we'll have 2r pi dr. Remember, 2r pi is an arbitrary length of one of these rectangles, and dr is the infinitely small width of these rectangles. So we'll end up all of these from 0 to r, which is right there, from 0 to r. And if we develop this expression, we can factor out as above pi. We'll get r2, the primitive function of 2r is r2, r0, which in turn is pi, big R 2 minus 0, 2, which in turn is r2 pi. Remember, r is the radius of this circle, and r2 pi is the area of the circle. So that's another way to think of it. I hope this video has been helpful to you, and don't forget to like and subscribe, and see you in the next video.